Hello, my name is Gonzalo Villa. I'm a PhD student at the University of Cambridge with Fernando Quevedo. And in this poster, I will describe our recent work on gravitational waves from high temperature strings. In this video, I just want to make a few remarks on what are the main ideas behind our computation. So what we want to do is we want to compute the shape of a stochastic gravitational wave background. This is a signal that arises in the very early universe. Very high energy processes source gravitational waves which reach Earth today, forming a superposition of uncorrelated signals arising from the different patches in the sky, and we characterize this sort of signal by their energy density, which is a spectral shape, is a function of the frequency. Um, an example of such a signal is the Standard Model. High energy process in the early universe released gravitons in this manner, and the Standard Model gives a concrete prediction at the frequency of around the 80 gigahertz. And the question here is whether string effects in the early universe can alter this conclusion. We reply in the affirmative. So we computed the gravitational wave spectrum that arises if one has a gas of thermal strings instead, and found that the amplitude, the gravitational wave amplitude arising from this gas of thermal strings, when compared around the same conditions with the Standard Model, gives rise to a larger signal. In order to do this, we had to describe string thermodynamics, and the idea is that as one puts energy into a system described by string theory, when one gets close to the Hagedorn temperature related to the string scale, there are two competing effects. So, as is well known, the energy density, the density of states of highly excited strings grows exponentially. But of course, in thermodynamics, there is a Boltzmann suppression with the inverse temperature 1 over with the inverse temperature beta. And so the equilibrium configurations feature a competition between this exponential growth of the number of states and the exponential suppression of the exponential Boltzmann suppression, which generate a new scale, which we call 1 over L here. And one can argue that this describes or this gives the typical length of a string in the ensemble. So what we want to do is to describe a gas of highly excited strings. In order to do this, what we did was to coarse grain over levels. So we took certain averages when computing worldsheet amplitudes. And this allows us to develop a kinetic theory. There are simple analytic expressions which admit a certain random walk interpretation that I'm happy to discuss. And so one can find equilibrium solutions and so on. From here, compute equilibration rates, which are very important in cosmology. And one can argue that there's computational control and thermal equilibrium whenever M string is much smaller than M Planck. This allows us to put the system in cosmology. So the idea again is that we have a gas of highly excited strings releasing a gravitational wave spectrum, and we find that the amplitude is larger. So this is one of the few examples in which a single stringy origin dominates, and I will be more than happy to discuss what's the intuition behind this result and any other comments you may have. So thank you very much for watching until the end.